I want to talk about the HR diagram for a minute. And the reason I do is because it's one of the most important diagrams in all of astrophysics and astronomy. More can be gleaned off of this diagram than I think anybody ever dreamed of or imagined. It has so many little sub areas where particular things go down, particular physics. But one of the things that I think is not appreciated about the HR diagram by a lot of astronomers is this amazing range of luminosities that stars have versus the very narrow range of temperatures they have. And I want us to think about that for a minute. And of course, that would be something you would cover in Jason's stellar structure class. But I want you to think about this in sort of a new angle of thinking about this HR diagram. Is my mouse big enough to see? Okay, because I can make it bigger, and I think I will in the future. From 10 to the minus 4, 1/10,000th of the luminosity of the sun to 1,000,000 times the luminosity of the sun. Now that's 10 orders of magnitude. Think about that for a second. In the power output of stars. Because that's what luminosity is, energy per second. This is the power output of a star. 10 orders of magnitude, right? 100 billion, a factor of 100 billion. So this tells you that there's this extremely wide range of energy budgets in stars. And yet their masses only range over maybe 2 orders of magnitude, from around just under a solar mass, maybe a half, rounded off, up to about 100, if you extend it to the very bitter end of what nature makes. So roughly 2 orders of magnitude. And temperature on the surface of these stars only ranges by an order of magnitude, typically somewhere around 3,000 up to about 30,000. Okay. So something is really interesting here. You have a small dynamic range of gravity, which results in a huge dynamic range, 10 billion, in energy output and energy budget. But somehow that energy, which could be 10 to the 6 times the sun or 1/10,000th the time of the sun, that comes out, the flux that comes out of these stars is within a very narrow range of temperature, only an order of magnitude. So you have all this energy in the core, which the total luminosity comes out of, because that's conserved, the energy per second coming out. But the surface temperature is only between 3 and 30,000 degrees. So there's something that's regulating stars that, even though they have a huge difference or range of luminosities and power output, that the flux coming out of the surfaces, the surface flux, doesn't vary all that dramatically. Does anybody want to say what's wrong with that statement? Let me restate. The order is only an order of magnitude variation in the temperature of the surface.
Well, you got sigma t to the 4th, right?
Bingo. So the flux really does vary a lot. So I kind of wrote this down. The temperature is a result of the surface flux. It's really the other way around. Well, I guess it's true. The temperature is a result of the surface flux. So the surface flux can be much higher in a high mass star, which has a high luminosity. It's just that because it has such a high sensitivity to temperature, temperature has a narrow range dynamically from the low mass to the high mass stars. So I'm just trying to get you to think about this backwards and understand why temperature doesn't have that large of a range on the HR diagram, even though luminosity has a 10 billion dynamic range. And this is all telling you about the physics of stars right here. I mean, forget taking a spectrum. The HR diagram has just told you volumes about how stars work. Bingo, right off the bat. So all these clues. Okay. So anyway, you've probably all seen that HR diagram. You probably understand why this is blue over here, because hotter things actually emit more blue light and cool things emit more red light. And you've probably been introduced to spectral types. We'll talk about those a little bit more detail. Not a lot. We're not going to do Corbellian gray level, but we're going to fly over that book real quick. And then you probably, in addition to spectral types, you have heard of luminosity classes, the giants, and this is related to the surface gravity. We'll talk about that. Any questions about that diagram? Excuse me. I hope I helped you see it a little bit new in a new light. Okay. We mentioned this in our first slide, the relationships between luminosity, temperature, and radius. It really comes down to the fact that luminosity is flux, sigma t to the fourth, per unit area, multiplied by the entire area of the surface area of the star, 4 pi r squared. So you multiply the flux per unit area by the total area of the surface of the star, bam, you've got the total amount of energy coming out of the star, which is its luminosity. And so it turns out you can solve this equation for R, and that's why if you get L and T, you can measure the radius of a star. Here's an example of some stars. Number 2 is Rigel. Number 2, Rigel, number 2 is up here, okay? And it turns out that you can draw lines of constant R, and then you can vary T and solve for L for constant R. And it turns out that Rigel is near this family of curves for R equals 100. And so here's Rigel, it's about 100 times the size of the sun. Again, I don't think I'm telling anybody anything new here, but we're just getting reacquainted with it. Let's look at Betelgeuse. Number 22 here, up in the supergiant range of the HR diagram, and you can see that it's got a constant, it's in the constant radius curve of 100 or 1,000. So relative to the sun, it's about 1,000 times bigger. And so I don't know who's seen this before, who hasn't seen it before, but there are these lines of constant radius on the HR diagram. And so if you go from the lower left corner, where you are low luminosity but hot, you are small radii. These here are the white dwarfs. R of 0.01 is the radius basically of the Earth, 1/100th of the sun. And these white dwarfs are all about the size of the Earth or a little smaller. So that's how we know these stars are small from L and T. Here's your main sequence, and then the red giants, the evolved stars. And so it's kind of an interesting diagram that, like I said, not only do you get this understanding between flux and temperature and energy transport and luminosity, but you also get radius. All right, this is what we were trying to do when we were doing our first question, what can you get out of spectra? Right, what can you get out of spectra? Again, I'd like to turn that and flip it on its back and make it go belly up and look at it from the other side. And that is, we were thinking, what can we get out of a spectrum when you measure it? But really what you want to do to understand a spectrum is what physical things create the spectrum and what physical things create if you turn the dial on some physical thing, how does it change the spectrum? Because things that do that are the things that we can measure from the spectrum. You see, it's just looking at it in reverse. Okay, so stellar mass is clearly a major component governing everything about stars. Okay, first of all, it governs the hydrostatic equilibrium profile of each layer because that's related to the density. The gradient is related to the density at each layer. Okay. That gives you at each layer the pressure. Ideal gas law, that means you get the particle density. You can get the temperature through the relationship of P, N, and T. P equals NKT. And then at a given temperature and density and particle pressure, you get ionization and excitation balance going on. And that governs what you're going to see in the spectrum. Okay. If you see an H alpha absorption line, what element does that come from?
Hydrogen.
What kind of hydrogen?
Hydrogen with one electron.
Neutral.
Okay, neutral electron. Okay, we're getting there. Anything more specific about that electron?
It's got to be an N equals 2 to start with.
Got to start in N equals 2. And then to absorb, be an H alpha line, the electron has to get knocked up to N equals 3.
3.
Okay.
Come back.
Okay, great. Well, does every hydrogen atom just sit around neutral, or are some of them ionized? Does every hydrogen atom sit around with its electron sitting in the N equals 2 excitation state? Or some of them in 3, some of them are in 1? Are you going to get an H alpha absorption if a photon comes up to a hydrogen and its electrons in the stage N equals 3? You're going to get an H alpha absorption line from that? No. That hydrogen's dead to you, right? Okay. So the excitation level and the ionization stage is absolutely critical for every absorption line you see in a spectrum. It depends upon a given element in a given ionization stage in a given excitation level. So if you want to understand the spectrum, you got to know that. You got to know that for if you have a line that comes from iron in the single ionized state of this transition from N equals this to N equal that, you got to know how you're going to get the total hydrogen. You know, you can measure how many of those particular atoms there are from the spectrum, but how are you going to go back and get the total amount of iron in the spectrum, in the stellar atmosphere? You've got to know ionization and excitation. Absolutely. Okay. And then it turns out that this is all coupled to the radiation field. So you have to account for the fact that the radiation field is what's being absorbed. Okay, and it turns out that it also will couple with the excitation and the ionization. Okay, and because radiation can ionize an atom as much as it can do a bound-bound jump of excitation. What about chemical composition? This is why we can learn about chemical composition. This is the green box says why we can learn about pressure, temperature, ionization, and radiation. The orange box below it tells us why we can learn about chemical composition, because that governs the entire particle field, its density. And the ionizations and excitations tell you how many free electrons are in the gas. Okay, and that tells you something about what your magnetic field properties can be like when you have free plasma particles like that. Ion molecular density, ionization, excitation balance, again, are all coupled in the particle field. Then you have the radiation field. It gives you ionization breaks. Does anybody know what I mean by that?
You get atom, say you have hydrogen, or I guess I'm thinking of galaxies, right? But if you have light that's more energetic than a certain point, right, it's going to ionize the hydrogen and get somewhat absorbed or scattered, or there's going to be
Right.
some sort of process and block it.
This feature here, which we're going to talk about a lot in this class, it's called the Balmer Jump or the Balmer Break. Boom. That's because, there's your 2 to 3 of neutral hydrogen, your 2 to 4 of neutral hydrogen, 2 to 5, 2 to 6, blah, 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 2 to infinity. But then 2 to infinity means ionization. And every photon that has energy greater than that energy that can ionize an electron gets absorbed by the neutral hydrogen. And so it causes this break of all these photons that just get removed from the line of sight. Okay, we call it the Balmer Jump. We'll talk about that in some detail. Obviously, the absorption lines, their strengths are proportional to the ion and excitation, as we just described up here. The continuum opacities, some of those are proportional to the electron density. So when we come back and look at these spectra, the shape of the spectra, whether it has this shape where it gets is very blue and is curving in this concavity shape toward the red, or whether it is flattened like this, or more flattened like the G stars, what causes those shapes to be different? Okay, well, one of them is the free electrons that are in the gas scatter light. And so those are important. Okay, then you've got the fact that these continuum opacities, which we'll talk about what opacities are, actually also depend upon your various ions that are present in the gas. We'll spend some time this semester talking about the H- ion. This is neutral hydrogen that has captured a free electron, which it can only do if there are free electrons in the gas, which means you have to have a partially ionized gas so that some free electrons are zipping around. Some of them get captured, and you have 2 electrons orbiting around a proton in what's called an H- ion. That second electron is very loosely bound. A photon can come in and knock it off. That photon gets absorbed. And since photons of a lot of different energies can do that, it changes the overall shape of the continuum of the spectrum over a large range of wavelengths. That's a very important continuum opacity. So all of this information is hiding in the shapes of the spectrum, in the relative strengths of the lines, and how deep the Balmer jump is or how shallow it is. All of that is telling you about the conditions that are going on in the chemical composition and in the physics of the gas. So you can look at a spectrum and you can read. The more you learn about it, the more you can read exactly what's going on in the atmosphere. Okay. We'll finish with this slide and then we'll come back when we meet on Thursday. Energy transport and opacity. The opacity, which I haven't defined, which I will define in our next lecture, is basically related to the mean free path of the photon. And so when you have a lot high opacity, that means that the photons only move very short distances before they get absorbed. And so we have what's called the continuum opacity at a whole bunch of different wavelengths that shape the shape of the continuum of the star. But it turns out that this opacity changes as a function of distance or height in the atmosphere of the star. And it depends on, guess what? All of this stuff. And so the opacity is in a circular logic loop with all of this stuff. This stuff is what makes the photons, makes the gas opaque to certain photons, which is the opacity. And the behavior of this is what gives you the overall shape of the spectrum. But in the end, what are stars? They're just energy transport machines. They take gravitational potential energy, they convert it into nuclear energy, which turns it into light transport, transporting light, electromagnetic energy that eventually escapes into space. So really all it is just this big energy transfer ball, okay? But all of this physical details going in it, and thank gosh they exist because we can exist, but we can extract all the information about the conditions in these stars. Okay, so one of the things that happens in energy transportation is that you get sometimes regions of convective turbulence. And this causes another form of line broadening. And so you can actually measure the turbulence rate from your absorption lines. We didn't put that in our original list of things you can measure. You can actually measure the velocity of the turbulence of the convective regions in stars as well because of something called a microturbulence broadening. Okay. And last thing we talked about were the Doppler rotations. You got your stellar rotation. This is actually Doppler effect too, because you've got gas rising toward you, gas falling away from you. Microturbulence is a Doppler effect. And then you've got, of course, rotations, which vary your line shape. Because those are things that make the features in a spectra, those are the things that we can extract physically from observing the spectra if we understand how to back the physics out. And that was the key, okay? But today I want to end up with an introductory tour of spectra. I think all of you at some point in time have been introduced to spectral classes or spectral types, O, B, A, F, G, K, M, and understand on the HR diagram, you've been introduced to that. So I sort of started there at the beginning of the lecture with the HR diagram, didn't explain it in a lot of detail, but here are some examples of some stellar spectra. And as we do often in the world, we see things, but do we observe them? We see that those spectra are different. They have different shapes. They have different patterns in them. But what are we seeing? In other words, do we observe them? Do we understand underlying what makes each of those stars have the spectra they do? In this case, these are all main sequence spectra. They're in the process of fusing hydrogen to helium in their core. And we are sampling spectra from the cool stars, the M3, up to the hottest star sampled here is the O7. And so I have a little note, a little bullet here list of things that you should probably always observe and think about when you see a stellar spectrum. Let's start at the bottom, the continuum shape. Okay, what do we see in words here? We see this O star has higher flux in the blue and lower flux in the red, so it's bluish, and this has a concavity that looks a heck of a lot like the red side of the black body curve. And you probably have all at least been introduced to the idea that stars underlying have a black body radiation curve, which is first and foremost the radiation generated in their atmospheres or equilibrium level. But if that's the case, then why is it when you go down here to the G star, you no longer have the same concavity? Notice that the curvature is different. It's more like an upside down parabola now, and it gets less flux in the blue, and then most of the flux in the visible center, and then less flux toward the red. And so the first question I have for you as stellar spectroscopists is, do you understand why that's happening? So the goal is that by the end of this class, that'll be second nature to you. you'll really understand why these spectra have different shapes in their continuum. And of course, since galaxies are made out of spectra of stars, when you integrate a whole bunch of stellar spectra by their distributions of their luminosities and numbers, you get out an integrated spectrum, which is a result of all of these photospheres. You also notice, for example, we'll go to the top bullet, the Balmer Jump. Now, we talked yesterday about if you have Balmer hydrogens, that's my shorthand for a neutral hydrogen in which the electron's in the n=2 excitation level. We'll call those Balmer hydrogens for short. When you have Balmer hydrogens, you have some photons that have high enough energy to ionize that electron. And it turns out that that's how here about 3646 or something like that. I can never remember the exact number. And so you might notice that you're removing all these photons that are ionizing Balmer hydrogens, but you don't see the signature of it in all the spectra, do you? Where do you see it the most strongly on here? You see it sort of in the B and the A star, sort of around 10,000 degrees. That efficiency, or the number of these things that are happening that are removing flux out of the spectrum, is a maximum around 10,000 degrees. So the questions are why? Why is that a maximum around 10,000 degrees? And some of you may argue, well, because if you get hotter, you start to ionize all the hydrogens, so you don't have Balmer hydrogens laying around, so you can't ionize them, and so you can't have a Balmer H. That's partially right. And some of you might say, as you go to cooler stars, more of the electrons are actually down in the ground state in what we might call a Lyman hydrogen for short, n=1. And so you don't have as many in the Balmer state, and therefore when you get cooler, you don't have as many around to ionize, therefore you don't see as many photons being removed. Well, you'd be half right again. There's more to it. There's a lot more to it. We'll get into that this semester. Why does the Balmer break maximize in an A0 star at 10,000 degrees? Okay. Okay. Then you might notice something about, we'll go to the third bullet, the Balmer line strengths, H alpha, H beta, H gamma, H delta, and H epsilon. Those are about as far you need to go down the chain before you get to something called the Balmer Convergence, whereas the lines start to come together so much that you start to see the flux curl over until you get to n=2 to infinity, and you get the ionization edge here. Okay, so you have a Balmer Convergence, you have the Balmer lines, and you'll notice the Balmer lines go from pretty strong, stronger, strongest, a little weaker, weaker, disappear. Okay, again, that's related to the number of Balmer hydrogens that you have available in the atmosphere. Okay, and apparently those tend to peak around 10,000 degrees. Okay, but it's not strictly because of the balance of excitation and ionization. There's a little more going on. Okay, now the other thing is the G band and the molecular bands and the calcium H and K. So what I've taught you today are the very, very basic things of what you see in stellar spectra. You can go miles and miles and miles deeper into them, but these particular features are what I would call the key surface features of all spectra. The G band is shown right here in this, what do you know, G star, but it has nothing to do with G stars. Okay, this is a CH band. So you have to be cool enough for carbon and hydrogen to bond in order to start to get this molecular band absorption here. And it's really kind of a pain in the butt because it turns out that it's just bluer of H gamma. And so you get to this point where there are some stars here between G and F stars where you can't really distinguish between whether you're seeing an H gamma line or the G band in noisy data. And so that's a little bit painful. But if you can just remember the H gamma is near the G band just a little bit blue of it, you're in good shape. If you know where to want to go look and find it. You have your titanium oxide bands. Those show up only in the coolest stars where you really are cool enough for titanium and oxygen to bond into molecules. Okay. A next tall tale sign is your calcium H and K. And then I didn't write it here, but you also have your sodium 1D lines. Okay. You can see sodium 1 gets stronger as you get cooler. Sorry about that. And calcium 2 has a situation where it also balances out. As you go to cool, you don't see the calcium 2 lines, but as you get a little warmer, you get the calcium 2 line showing up. And then look at this little doozy here. Here's this beautiful calcium K line and this beautiful calcium H line. And then you come up here and you got your beautiful calcium K line. Whoa, what happened to your H line? Did it get bigger? No, that doesn't make any sense because those two lines depend upon the column density of calcium 2, ionized calcium. So this is a blend with our friend H epsilon, which is not shown here. So as H epsilon's getting stronger and the calcium lines are getting weaker, you hit this spot where the calcium K line, you can see it, but the calcium H line is completely wiped out by H epsilon. Any questions about that? Next slide. Has anybody ever seen this before? Nod, 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 raise hand. Yes, yes, yes. Okay. Right, your beautiful energy diagram of neutral hydrogen. It actually is a highly simplistic version of it. Later on, I'm going to show you a true energy diagram of neutral hydrogen, and it is way more complex than this, though this is really what gets taught to people until they really try to become a professional. So we're going to try and take you to the next layer. But you all know you have a ground state electron, n equals 0. That has 0 excitation energy by definition. It's at the floor. Okay. And if you excite that electron, it can go up to the n equals 2 state. That corresponds to the Lyman alpha line, which has a wavelength of 1215, n equals 1 to 2. And that's written here in this chart. That's Lyman alpha, Lyman series, starting at n equals 1 and going to n equals 2, if you're following my arrow. And that's 1215, 67. So that's how you read the chart. This is the series of lines that come from the ground state up, and this is the other end for the upper state. Our Balmer hydrogens are those where the single electron is here, and then a photon at 65, 63 angstroms can move it up to n equals 2, or that's H alpha, or 48, 61 angstroms can move it up to n equals 4, et cetera, et cetera. And so I've labeled those in the Greek letters here for you. Alpha, beta, gamma, delta, epsilon, and then after epsilon, people start just counting them. Okay, so a lot of times you'll see up to epsilon marked in a spectrum, and then you might see Lyman 8, Lyman 9, Lyman 10. Okay, and then we have the Paschen series, which is if you have electrons in the n equals 3, a photon out here at 1.8 microns can in the infrared can knock you from 3 to 4. And so that's this entry here. This would be Paschen alpha, beta, gamma, blah, blah, blah. Okay. This is a homegrown diagram. I have a little caveat here in my drawing of my stellar spectrum. Stellar spectra do not look like this. This is a schematic. Okay. But what I'm trying to show here is these regions of the spectrum that correspond to these different transition regions of energy for the hydrogen atom. Okay, let's start with n equals 1. Here is your Lyman alpha line. Here's your Lyman beta line. We're in the ultraviolet. And then you have your Balmer convergence, and you have your Lyman jump or Lyman break. Okay, now, then what happens is this area of photons that are capable of ionizing Lyman hydrogens, n equal 1 hydrogens, that's called the Lyman continuum. Okay, let me say it again. Photons that are capable of ionizing Lyman alpha and above, or I should say n equals 1 and above, photons which are capable of ionizing neutral hydrogen that's in the n equals 1 stage, those photons are called the Lyman continuum. Okay. Now, interestingly, let's go now to the visible region of the spectrum. Here's H alpha, here's H beta, gamma, delta, epsilon, and then we stop. We get this convergence of these lines, start to wipe the flux out, and then we have the photons capable of ionizing Balmer hydrogens. Here, we call that the Balmer jump. And this area here is now called the Balmer continuum, because these are photons capable of ionizing hydrogen from the Balmer state, n equals 2. So you get the point here. When you talk about names of continua, you might hear this in a talk. You might have heard it before and not picked up on it, but you might now that you've seen it. You'll hear a talk and somebody say, well, in the Balmer continuum, and you'll probably be thinking that's probably in the visible part of the spectrum, and you'd be wrong, because that's the continuum of photons capable of ionizing n equals 2 neutral hydrogen, which is actually in the ultraviolet. Okay, let's go to the infrared. This is the Paschen series, and it's in the Brackett continuum. So here you have Paschen alpha, beta, gamma, delta, et cetera, et cetera. You have the Paschen jump. So these are now photons capable of ionizing n equals 3 neutral hydrogens. So it's called the Paschen continuum. So interestingly, the UV is the Balmer continuum. The optical is the Paschen continuum. It's weird, I know. Okay. So here's my little call-out box. The continuum is named after the n level from which these photons can ionize the atom. Okay. Example, n equals 2 ionization is the Balmer continuum, but the Lyman series line reside in that wavelength range. So it's not named after the bound absorption lines, it's named after the photons that can do the ionization. I will never talk about this again in this whole class. You probably will never see it again in any class, but there will be times where somebody will say it in a talk, or you'll be in a conversation with somebody, and you'll know exactly what that terminology means. And that's important. It's important to log that information in your head. The visible part of the spectrum, ladies and gentlemen, is called
Paschen continuum.
Thank you, Bryson. Bryson has exhausted all of his responses for this class period. Somebody else must respond. Okay, quick and dirty spectral typing. This really is a fairly crude, basic, undergraduate level exercise. When people type stars, they don't type them this way. But it's what I like to call your quick and dirty armchair spectral classification. You look at a spectrum and you just go through this little list, okay? Are there H lines? Yes or no? If there aren't, what's the ratio of the H gamma and the G band? Remember, they sit right next to each other. If they're about equal, you got a G star. If the H gamma line is much smaller than the G band, then you're probably either a K or an M star. Do you have TIO bands? Yes or no? You're an M star. But it's very, very simple. And you can actually look at that page of Spectra I showed you already, and you can see that this works quite well. The thing that he does not have on his chart, this is out of his book, and I added it here, is that you still get somewhat of a Balmer break in a B star, but you really don't have a Balmer break in an O star. And he left that out of his chart, so I put it in for you. So if you have H lines are present, yes. Do you have the K line? K line, calcium 2K line. Remember that line we showed you? If it's not present, then we're an O or a B star, so you should go look at the Balmer break. Here are the things that are important to look for in terms of this chart. H alpha, 65, 63, H beta, H gamma, H delta, and epsilon. Those are H lines. He doesn't really talk about sodium, but I put it in here. Your sodium doublet, 5895, 5888. And then your G band, which is right here next to, it should be down below it, just blueward of your H gamma, 4308. It really belongs, that arrow really belongs down here. And then your calcium H line, which is basically blended with your H epsilon, and then your calcium K line. And then way down here at 3646 is your Balmer break. Okay. So those are things that you should probably, as an astronomer, like as a minimum, know about stellar spectra. Like you should, like those should be part of your everyday speak, that at a minimum. Now, if you're going to go on and do apogee spectra and study them like Sten Hasselquist did, you're going to learn a heck of a lot more. Okay, so we can apply this real quickly. Let's look at this M5 star. Okay, H line's dominant, negative. Is the H to G band ratio? No information. So let's go to the next layer. Are there TIO bands dominant? Yes, M star. Okay, so it's not that hard, right? Let's look at this K0 star. Okay, are the H lines dominant? I'd say no. So we go down this road. What's the ratio of the H gamma to the G band over here? Looks like the G band dominates to me, right? So G band dominates over H gamma. So we're going to go over here. Are there TIO bands present? No. Okay. Bada bing. Pretty simple. Harrison Cook has raised his hand.
Oh yeah, quick question. So in this flow chart, the H lines is referring to the hydrogen lines, not the HK doublet of calcium, right? That's separate.
Yes, I know.
Okay.
I know it's ridiculous, but this is the way he wrote it up. If I was to rebuild it, I would make it more clear. But good question. H lines at the top there, it does not mean calcium H line. It means hydrogen lines. And but when you get down here, he is talking about what the K line is doing relative to the hydrogen lines. Okay. Same here. H gamma, in particular, H lines. And in particular, though, when you get here, you're really going to be looking at what's going on with H epsilon relative to the K line. So it's a little bit confusing. Yeah.
Got it. Thanks.
All right. So G star, you know, we could do this all day. G star, H line's not dominant. Nope. H gamma is about equal to the G band. Okay, so here we go. H line's not dominant. H gamma equal to G, G star. Need I continue? I think you all get the point. We don't have to necessarily go through every example. Here's some more examples where I've, because obviously these were cool stars, plus an O star down here. Oh, we could do the O star. Are the H lines dominant? Well, they certainly are there. Okay. And I would say they do dominate compared to the other lines, right? Okay. Is the K line present? So the K line is right here. You come down, I don't see it. That's a no, okay? And then you should be looking now for the Balmer break. And as I said in my previous version here, which I didn't attach to these other ones, here's where you should ask about the Balmer break. And in fact, there really is no Balmer break. There's basically a Balmer convergence, which does a reduction and then you recover. So that's an O star. Anyhow, I do a similar thing with these A5, F5, and F0 stars. You can go through that on your own. And I did an example for the G, K, G0, and F5 star here, or F5, G7, and K4 star. And again, I really love this. The shape of the continuum to me is more fascinating. You see this sort of beginnings of a black body, and you see this tend for a curvature, and then this peak and this de-reddening and de-bluing, if you will. And so I want to talk to you a lot about the shape of the spectra. I got two hands. Who was first?
Mark, go ahead.
I was just going to say, do you use the continuum? But it sounded like you sort of answered my question as you ended that discussion.
When we get to our third lecture, we'll talk about the Morgan-Keenan spectral classification system, and we will talk about the fact that you do not use the color of the star. You do not use the shape of the continuum. And we'll talk about why there's two reasons for that. Okay. Interstellar reddening being one of them.
Reddening, yeah, reddening.
Adam.
I didn't catch what the K line was.
So here's the calcium 2. The blue line is the K line. And the red line is the calcium H line. So the sodium doublet, and we'll talk about why you have doublets coming up. The sodium is a doublet, and it's called D1 and D2. That has to do with historical Fraunhofer lines, where Fraunhofer just gave them letters from left to right, okay, or from strength in the sun spectrum. And he called those D1 and D2 because they were so close. When it came to calcium, he called the blue one K and the red one H. So that's just old Fraunhofer, gibberish. Here's an example. Calcium K and H, K, H. But it's the H line that will blend with the hydrogen epsilon line. They're only within an angstrom of each other. Okay. Here I should have showed you this, Adam. Here is a blow up of some B5 to A5. So these are fairly hot stars, showing your calcium K line getting stronger as you get cooler, and also showing your H epsilon line dominating entirely over the calcium H line. You can't even see it because it's wiped out by the hydrogen epsilon line. But if there was no hydrogen there, you would see a doublet, a very narrow thin doublet. Okay. Any other hands? All right. So I'm just taking a quick fly over here. We're going to talk later in the quarter or semester about this pressure broadening. also known as luminosity effects. So let's look at these star spectra right here, stellar spectra. In the top, we have a B3. It's called a supergiant. So this is obviously a very large radius star. And the middle one is a B3 giant, so it's also a large star. And then the other one is a B3 dwarf. Now, for those of you who may not be familiar with the nomenclature, historically, a dwarf means a main sequence star, okay? So when you hear people saying, oh, it's an M dwarf, main sequence, okay? The fact that these are B3, which is a refined designation of its spectral type, is strictly a, well, not strictly temperature, but you could think of it as these are stars that all have the same temperature, okay? But strictly they don't exactly, but they all have B3 designations, and they're effectively all the same temperature stars. So why are their lines different in size and shape? Your dwarf, this is the H gamma line from hydrogen. Your dwarf has a very large equivalent width. We'll talk about what that is later, but has a large strength, and its wings kind of come out, you know, in this sort of strange upside down curvature. You see a similar situation with the B3 giant, and then when you get to the supergiant, those wings have basically disappeared and the line is narrower. Adam, you are very patient, thank you. I don't notice the hands right away. Question?
Oh, I forgot to put my hand down. I'm sorry.
You fooled me, okay. So giant stars have lower pressures in their atmospheres and their lines are narrower, okay? So the gas is much lower density in the atmosphere of a supergiant star. When you have a main sequence star, it has the same temperature of gas, but the gas is much denser, okay? So the pressure in that gas is higher. All right, so dwarf stars have higher pressures and densities in their atmospheres. Supergiants are bloated and they're thin, and so they have much lower pressure and densities in their atmospheres. So why is it when you have a low density, low pressure atmosphere, you get narrow lines, and when you have a higher pressure, higher density atmosphere, you get broadened lines? That's my little red Y. I'm taking questions, I'm taking answers, not from Bryson. Eric's got both his hands up. Oh, he's frozen. Poor guy's internet must be frozen. Nobody?
So it's from,
Smear.
well, go ahead, Samir.
So, I mean, well, pressure is from the. Wait, I'm sorry. Could you repeat the question?
Sure. If you come down to this little area down here, you see that the higher, this is a high pressure atmosphere, and this is a low pressure atmosphere. So the broadening increases with pressure. And it turns out that this is related to the relationship between the mass and the radius of the star, because the surface gravity, gravitational acceleration of the surface depends upon the mass and radius at the atmosphere. Pressure goes as that to the 1/3 power, and broadening scales with pressure. And my question is, why does broadening scale with pressure? It's not an easy answer, and if you don't know it, it wouldn't surprise me.
Well, if I had to hazard a guess, I feel like it has to do probably with some fluid effects on the atmosphere.
Yeah, it's a nearest neighbor effect, sort of like when you're in partially ionized gas. It's an electromagnetic soup. And if you are moving around in it, you are influenced by particles that have electric charge and therefore generating electric and magnetic fields, that you are influenced by those local electromagnetic fields. They cause a blurring in the energy levels, okay? And they actually could cause splitting in the energy levels, and they can cause a blurring in the energy levels. And so the n=2 state is not, in this case, it causes splittings, but the n=2 state is more complex because of electrons that are flying by nearby are causing impulses that mess up the energy levels of the bound electrons. And so they call this pressure broadening. And there's multiple kinds of it. You'll hear about it later. There's called linear Stark, quadratic Stark, van der Waals, and resonant. They're all 4 different forms of pressure broadening we'll talk about. So I just wanted to bring those up. Harrison.
So this is different from Doppler broadening, which is due to like the velocities of the atoms.
Correct.
Due to pressure. Okay.
Correct. Well, the velocities of atoms is not due to pressure as much as it's due to temperature. But pressure and temperature are proportional. Correct. But the Doppler broadening is due to the kinetic speeds and the line of sight dot product with this kinetic speeds, the distribution of kinetic speeds of the particles, so that you get blue shifted absorption and red shifted absorption because particles are moving toward you and away from you. That's a completely different effect than the actual inner workings of the energy structure of hydrogen being modified by the electromagnetic impulses of near what I could call near collisions, okay, of electrons and other protons and hydrogens and things like that. So it's very different.
Okay.
Also, Harrison, the thermal broadening induces a Gaussian broadening shape on the absorption line. We'll talk about this later, but you brought me right to this graph here, where the thermal broadening is still reflected in this core of the line, and it's a Gaussian kind of shape. But you'll notice that the broadening, due to pressure, is this kind of flaring wing. And this function is called a Lorentzian. Many of you have probably seen Lorentzians at some point. And so the wings of the Lorentzian here are what dominate all the light that gets removed. So these are actually Lorentzian wings here. And it's stronger when the pressure goes up, because as the pressure goes up, you have more nearest neighbors. They spend more time near each other. Their electromagnetic soup influences each other more. And then my last slide, second to last slide, is just showing this effect again in an A star. So here we have a beautiful A star suite of spectra with H beta, gamma, or delta, gamma, delta, epsilon. Here's your perfect example of your calcium K line and the H line being blended with the hydrogen epsilon line again. Then we have our Balmer limit. And you'll notice here's our dwarf star, and it has the biggest lines, but the giant star has less strong lines, and the supergiant has the weakest lines. Yet they all are basically almost the exact same temperature. It's because the pressure in their atmospheres are different, and the dwarf stars have much higher pressure and densities. So Harrison, for example, the thermal broadening of all these stars is almost identical because their temperatures are all almost identical, give or take a few degrees here and there. But the pressure broadening is very different between them. And last but not least, we'll spend a lecture on rotational broadening. And this is a situation where stars are rotating, and this is a Doppler effect where the limb that's rotating toward you, if I get that in the camera right, the limb that's rotating toward you, you get blue shifted absorption. The limb that's rotating away from you, you get red shifted absorption. That's what's being shown in this picture to the right. And so these are shortened wavelengths. They get bluer. These are lengthened wavelengths. You can see here that they've shown that by showing you longer wavelengths and shorter wavelengths here in this picture. And you get this broadening of your absorption line. Whereas if your star is not rotating, then all the photons come out and your line really has the shape of the physics of the atmosphere only, and you get this narrower line. And so in fact, in addition to pressure broadening, in addition to thermal broadening, you can get rotational broadening, okay? Here's an example of a template star with no broadening, no rotational broadening, okay? Here is a function that you can convolve, or if you convolve it with a rotating star with V sine I of 40 kilometers per second, I mean, it's rotating such that the projection of velocities is 40 kilometers per second. You don't know how tilted the star is, you just know the line of sight component to the velocities are 40 kilometers per second. And it looks like you recover what looks like the star 404 Cygni. And so we would argue then that if 404 Cygni was not being rotationally broadened, that underlying spectrum would look like this. So rotational broadening can do a lot of damage to spectra. What I mean by damage, I'll say that once in a while. Oh, that does a lot of damage. That means it has a strong effect. But when it comes down to it, how do you model any spectrum? And you get these undulations of line shapes. And you have certain physics that you have simple models for how lines get modified. Rotation models, thermal broadening models, pressure broadening models, okay? And maybe even flow models, like outflow models, you know, that cause some kind of thing. And what you do is you basically try to chi-square fit your data, you putting in all your free parameters into your models, and then you try to find the free parameters that produce back to you the spectrum that you observe.
Yeah.
And then you pull out your parameters from your models and say, I think the temperature is this, and the gravity is that, and the chemical composition is this, and the microturbulence is that, and the rotation is this. You know, hopefully you don't get too many free parameters.
Yeah.
Okay, so, but this is just an illustration saying that if you took the template and convolved it with the V sine I model of 40, you get the red spectrum. And then they're showing you a model, or they're showing you an actual spectrum, which happens to mimic it. So I think for the illustration, they were trying to get 404 Cygni back, you know.